thank you for replying to this questionnaire. So there are several questions that you wish the lecturer would answer, and I will try to answer to those questions if I have not done it already during the rest of the lecture. But please don't hesitate to ask more questions. So among those questions, there is a question which I found very interesting, which is, well, there are many interesting questions, but the one is why is this? Oh, yes. Why are there many formalisms in quantum field theory? And that's a very interesting question. I want to say a few words about that before continuing discussing what I started to discuss yesterday, which is the structure of the behavior of a quantum field theory at short distances in space-time. So, well, the one who asked this question means that we think there are three different formalisms. I don't know very well what are the three ones, but I can imagine that you are thinking about first canonical quantization to define what is a Hilbert space and what are the observables of a quantum field theory. The second one is functional integration or path integral formulation. And I presume that the third one is functional integration or path integral formulation in Euclidean time. Or do you know another one, another formalism? So what I want to say is that, in fact, you should not really think about the way one computes in a quantum theory as a different formalism, but as different representation of an underlying theory, which is a unique mathematical and object and a unique, in my opinion, way to represent what we can do, what we know, and what we can measure about the universe, including us. So, and I mean representation in the sense of, in the mathematical sense. You know, you have seen, if you know some group theory, that you can consider a mathematical object which is just a group, like the group of rotation or the group SU2 or a group of permutation of objects. You can represent them usually as a group, a set of transformation acting on something. For instance, the group of rotation is a group of transformation where you have a vector and you move it, you turn it around in physical space. But you can also think about a group as just a mathematical object, you know, a set of group elements endowed with some rules. You know, for a group, it's a multiplication. You take two elements and you combine them in some order. Namely, you multiply the first element by the second order, and you get another element of the group. And if you know a few rules of consistency, this defines a group, independently of the way it is represented. And finally, you know that for a given group, you can represent it in many different ways. For instance, the SU2 group, you can represent it as acting on one half spins or one spin, so you have different representation of the group SU2 acting on different vector space. But as long as you are just only interested in the properties of the transformation, so there are different representations of the same object, which is a group. Okay. So in fact, it's a bit the same in a quantum theory. In a quantum theory, in fact, what you are interested are the two basic objects in a quantum theory are the observable of the theory. Okay, what you can measure, what you can do on a theory, and the states. The states is how can you represent the present state of some system, or at least what you know about the present state of a system, of a quantum system. Okay, so in quantum theory, those are more subtle concept that in classical theory, but those are well-defined sets. And then you have to think how you can represent this object by a mathematical formalism, because after all, physics is, in fact, as Galileo said once, is the language of the world, and therefore physics is mathematics. So physics is the way how we can represent what we observe, what we know about the world in terms of logical, therefore mathematical laws. So observable, we know that in quantum physics, in fact, observable can be represented as operators acting on some Hilbert space H, and states can be represented, at least for pure states, as vectors in this Hilbert space. And that's the basics of the canonical formalism. Okay? But what's important, in fact, is just that you want to be able to compute some matrix element, namely where you have some in-state, some initial state, some observable, let us call it A, and then some final states. And you want to compute some probabilities, transition probabilities, or probability amplitudes to measure that. And that's what you want to measure. You want to compute numbers. And in particular, what you want to compute is when the in-state and the same the out-state, then you will get simply the expectation value of the observable in a given state. So you know what is the average number of you get out of a measurement of an observable on a given state. Okay? And so in the canonical formalism tells you that you can represent this simply as a matrix element of the operator acting on the Hilbert space of states. Okay? But so that's the canonical formalism. Okay? In the path integral or functional formalism, you can represent this simply as a sum over some histories of histories where you start from some initial boundary states, you go to some final states, so you have something like that. You see, as a function of time, you have something like that. You start from an initial state, you go into an initial state, and with some weight, some weight, S of the history. And then you have the observable is something which depends on the path where you are. The observable is represented by what's happening at some time. So you see, for instance, you start from initial time to an initial final time. This defines you the evolution operator between the in state and the out state. And if you are interested in if the observable A is just the position of the particle at a time t, given time t, what you have to do is to sum over histories and take the average over the sum over histories with, of course, an I factor because I am in quantum theory. What is the average over with the sum over histories of the position of the particle at this given time? So that's another representation using path integral of the same physical quantities. You see? But what's important, but it's not very, so those are two different representations in the mathematical sense of the same quantity, you see? And quantum theory is a theory which is both rich enough and consistent enough so that you may have seemingly different representation of the same object by formalism which looks very, very different. But they are mathematically interrelated, and at the end you get the same quantity. So you simply have to choose which one is the most convenient to understand, to have a good view of what's going on, and to compute. For some theories and some quantities, it's better to use the canonical formalism, and for instance, to solve the Schrödinger equation. For some problems in some class of theory, it's faster and better to use a functional integral formalism because you go more quickly to the results, or you get a better understanding of what's going on, you see? But those are different representations of the same theory, and therefore not completely different formalism, you see, just different representation. Okay? So this will be important in what I will be discussing, because you have to, in the following, I will start to consider what is the behavior of the observable of the theory of a quantum field theory when those observables correspond to objects, to quantities you measure with a very short time interval or at distances which are at points which are very close together. And you must keep always this picture that what we are interested in fact are just expectation value or probability amplitude between some states of one observable of the theory. Okay? So, and finally, in fact, the connection between the path integral in real time and in imaginary or Euclidean imaginary time is just, in fact, those are two mathematical aspects of the same formalism, because the path integral formalisms, once you compute the path probability amplitudes via the path integral formalism, you realize that, in fact, you can compute this object both for a time which is a real variable, and then by analytic continuation for a time which is imaginary, and this is something which is convenient, both convenient for the calculation and to make connection with statistical mechanics. Okay? So in fact, there are the path integral formalism in real time and imaginary time, that's just two parts of the same formalism or the same representation, and canonical quantization is another representation of quantum theory, which turns out for quantities where the theories where we can compute both of the same, gives the same physical quantities, which are the transition amplitudes. Okay? Or the matrix element of operators. Yes?
So there is, from the path integral point of view, a correspondence between path integrals and a classical statistical mechanical system, which you should...
Yeah, often. Yes.
Yeah. So, I mean, is there any deep connection? Is that something that we can see, for example, also in the canonical formalism, that connection?
There are some quantities in the canonical formalism, what is important is the evolution operator U of t, which is the evolution operator. Okay, and I think you have seen in statistical mechanics and in one of the tutorials we have seen that you can treat some problem of statistical mechanics on a lattice by a transfer matrix. Okay, you have a system, for example, you have Ising spins on a chain, classical Ising spin on a chain, and in fact, you can define an object which applies the set of all possible states at a given point to the other one. You see like that. So this transfer matrix, this set of matrix acting on the states is in fact the analog of the evolution operator. So there is also an analogy between what's happening in real time and what's happening in imaginary time in the canonical formalism. But I don't want to elaborate further at that stage. But usually when you have something in one of the representation of quantum theory, so some properties, it has its analog in the other representation of quantum theory. It may be something complicated here and something simple here, or something simple here and something complicated here. But in general, since those are two representations, you can always represent something in the both formalisms. You see? Okay. So now let me come back to what we started to do last time. Okay. We realized that we were interested into the phi-4 theory, so we are considering the phi-4 interacting theory. Okay, and we realize that when we are computing in perturbation theory at one loop, namely first order in h bar, order in h bar in the quantity, we found some quantity which had some what we call ultraviolet divergences, which mean simply that you have singularities occurring from the fact that you are integrating over expectation value of some operator at short distance in space-time. Okay? divergences. Sorry. Okay, and therefore we want to analyze those divergences further. And to analyze those divergences, I will go back to the free theory, so a free field, because after all, in perturbation theory, you are computing observable of the free theory in order to compute. So you are computing expectation value in the free theory of products of operator. So I will go back to the free theory, which is given by this, remember this action. So let me call the Euclidean action phi of is d. So let me consider that I'm now in the d-dimensional dimension of 1/2 of d mu phi plus m squared phi squared over 2. This is the action. So it's just a free field with a mass m. And we have seen that if we are computing the expectation value of the products of two field operators between 2 points, let us consider that one point is at the origin. So this is phi of x, phi of 0. So this is in Euclidean space-time. We have seen that this behaves like some constant which depends on the dimension, time, something which is just, in fact, so let me call this is x squared, the modulus of x, of the vector x, and there is a power which is just 2 minus the dimension of space-time divided by 2. So d is the dimension of space-time. Okay? Okay? And and this, you have singularities as long as d is larger or equal to 2. You have, it's infinite at x equals 0. See? And this singularity, as I explained to you, is present both in Euclidean space-time, so in Euclidean metric, in Euclidean where x squared is just x0 squared, well, x0 squared plus x d minus 1 squared, and in Minkowski space-time, where what I call x squared is with my notation minus x naught squared plus x d minus 1 squared. Because in both cases, this vanishes when all the coordinates are equal to 0. You see? Okay. So, this singularity means, the existence of this singularity means in particular that there is an important difference between what's happening in a quantum field theory in 2 dimensions or in more than 2 dimensions and what's happening in ordinary non-relativistic quantum mechanics. In quantum field theory, you would like to, so we know how to define the field operator. So we know how to define an operator, which is the field operator phi of x, as an operator acting on the quantum state of the theory, or as something we can compute its expectation value by the way of path integral formalism. We can define the field operator at a given point in space-time. Okay? But the question is, can we define something like the product, the square of the field operator at the same time? This is well defined, but this is not well defined. Okay? Because simply we have seen that if we want to compute the expectation value in the vacuum of the products of a field operator by itself at the same point, this is infinite. So in fact, it is not well defined because if we compute already in a free field theory what is the expectation value in the vacuum of phi squared, you find that something is infinite. Okay? So does it mean that in a quantum field theory only this operator is defined as a local operator associated to one point in space and time? Is there only one operator acting on the space, on the states of the theory that you can associate to one point in space-time? That's of course that it cannot be the case. Otherwise, it would mean that the Hilbert space of a quantum field theory is very, very simple. If you have only one operator acting, and you cannot build an interesting Hilbert space if you have only one operator acting on the vacuum, because one operator acting on the vacuum creates some state, and if there are no other operator, it means that your Hilbert space is basically as dimension 2. There is a vacuum and there is another state. And that's not the case. We know that there is an infinite number of particle states, etc. Okay. So there are, of course, other operators than the field operator in the quantum theory, but it means simply that you have to work a little bit more about that, okay, to construct them. And in fact, the correct formalism to study what is, to see how you can construct other local operators. So we want to compute more general local operators, O, that I can associate to a given point in space-time. And in order to construct and to understand what are the properties of local operators in a quantum field theory, in fact, the correct object, so it took some time to people to construct them. They started in the 50s by studying renormalization theory. But the correct way to view that, in fact, goes back to, I think, the end of the 60s, the beginning of the 70s. And it's called the short distance operator product expansion. And it's a very, very important feature and a very important tool in quantum field theory. It's associated to the name of the physicist Ken Wilson. And it's called usually simply denoted by OPE for operator product expansion. Okay, and I will explain what it is on the example of the free field. Okay, so imagine that we want to define an operator which looks like the product of two fields. You see? So what do you do to do that? In fact, in order to do that, let us consider that you have in space-time, you know, here is my space and time. Okay? And I am interested, I have a point x here, I have a point y here, and I want to define something which, an operator which defines simply what are the properties of those operators where they are very close together. You see? So, I am interested in, I have a point x. Yes? Pardon?
Would you be able to explain in a bit more detail why that's not well defined?
Simply because if I want to compute the expectation value.
Well, I understand what that's going to be.
Well, but this means that if I take this is an operator, you know, view it in the canonical formalism. This is an operator, a big matrix, acting on the space on the Hilbert space of the states. Okay? So since it's a matrix, I can multiply it by itself. I get the square of the matrix. Okay? It's another operator. And I want to compute the matrix elements of this this operator. Okay? So the simplest of the matrix element of this operator is simply this is one of the matrix elements of the operator phi square of x in between the vacuum state. It's the simplest of the. Okay. And if I compute it using either Wick's theorem or using the path integral formalism, I find that this matrix element is infinite. So it means that this operator is not well defined. You know, all the matrix elements of physical operator must be finite. You cannot have, this is a probability, you know, this is the expectation value of some, you measure something on the vacuum and you should get a finite result on the average, otherwise it doesn't make sense. So it means that, it means simply that, this doesn't mean that there is nothing associated to that. It means simply that all the matrix element, the matrix elements of phi of x squared, consider as the operator, some of the matrix elements are infinite. You see? So, now, which means that we are interested in computing some matrix element between some states, let us call it out, some states, initial state in, of the products of now two field operators at two different points. Okay? And we are interested into what is happening when x goes to y. So what's happening to this object when x goes to y? How is it behaving? Or y goes to x, let's say. Okay? The question is, are there some specific feature to this matrix element which is well defined when y goes to x? Okay? So, in fact, in the free field theory, you can construct all the matrix elements of these operators out of the matrix element where you have the n. Okay? In fact, it's enough to consider the matrix element where you have the operator phi x, the operator phi of y, and some other operators at any arbitrary point in space-time. Let us draw it that way. So you can add. You had a field operator here, a field operator here, a field operator here. Okay, and with if you know all those expectation values of those in the vacuum of those fields, in fact, you can reconstruct all the matrix elements of the quantum field theory. Okay. So the question is now, we are interested into, can we say something about the behavior of such vacuum expectation value of products of operator in the free field theory? So now I am dealing in the free field theory, so I put always 0 here to denote that this is a vacuum of the free field theory. Okay? And yes?
Is it does it matter that there is no time ordering on the left side? Because
well, it doesn't matter here because I have, for instance, I have assumed that x
is time ordered.
Is ahead of y. I can replace it by time order. Otherwise, I use the commutation relation of the operator to make it time order. Okay. So I want to understand what's going on here. I want to understand the behavior of this object when y goes to x. Okay? So for that, you can just use Wick's theorem. Wick's theorem, remember, tells us that such a matrix element, such a vacuum expectation value of the products of field operator is given by a sum of Feynman diagrams, which in the field theory are just pairings of a products over the pairings of propagators, namely this object, this Feynman propagator, gf of x minus y, where gf of some x, let's just say some x, some z minus some z, where gf of z minus z is simply, so z alpha, z beta, let us say, where the z's can be x, y, or any of those z, is simply given, remember, by represented in that way. Here I have the point z alpha, here I have the point z beta. Okay? And it is precisely this object. This is gf of x0. okay, which is divergent. Okay. So now, if you think about, let us consider the case where you have, well, let me drive it here. Let me consider the case where I have only two. Okay, so I am considering an object where I have x. You see, here I have the point x, the point y, the point z1, the point z2, and I'm interested in what's happening when x and y come close together. Okay? So in fact, in this sum, you have three diagrams, and you have this diagram, z1, z2, plus this diagram, x, z1, y, z2, and you have finally this diagram, x is connected to z2, and y is connected to z1. You see? And you see that in this class of diagram, if you are interested in what's happening when x goes to y, or y goes to x, so what's happening when those 2 points come close together, this diagram will contain a singularity, because it contains this propagator, which is singular when y goes to x. And those diagrams are, in fact, the contribution of those diagrams is perfectly regular when x goes to y, where y goes to x. You see, x and y staying stay far from z1 and z2. You see? Yes?
But then you have like
You have?
like if and y become the same thing, then you have both z1 and z2 interacting.
They are interacting, of course, but this propagator, z1 and z2 stays at a finite distance in space-time from each other. X and y stays at a finite distance from each other.
But do you not get a vertex with two legs coming out of it?
Pardon?
Do you not get a vertex?
So I'm just looking at this expectation value of these products of four fields in the vacuum theory. Yes?
But yeah, she's right. You would represent phi squared as a vertex with two legs. Phi squared at x as a vertex, so like an operator acting at point x, but actually would have.
Yes. So it means at the moment I have not yet decided how to represent phi squared. I'm just considering this subject, and I'm trying to define what is an operator which is like phi squared. You see? Okay? So you see when y goes to x, this contains a singularity. This is regular. But on the other hand, this object is the quantity associated to this part of this theorem is just g of g Feynman of x minus y times g Feynman of z1 minus z2. You see? Because it's disconnected. So it's a product of something which is singular when x goes to y times something which is perfectly regular. You see? So when x goes to y, you get the singular contribution, which is z1, z2 times something that I represent like that. So this is singular, this is singular, this is tenuous, and this is regular. This is fine. We should represent it as something red, green, because greens means that it's something which is perfectly smooth, regular, and this is dangerous because it's infinite. It's the quantity is computed here. See? Okay? And then we have two other Feynman diagrams. The Feynman diagram like that, plus another Feynman which is the same, in fact, like that. So we have two times the same Feynman diagram. Two. This is now x, this is x, this is x, and those are also the sum of Feynman diagrams which are regular as long as x is different from z1 or from z2. Okay. So this is regular. Regular. This is regular. And this is singular. Okay? So, and therefore, in fact, it's tempting to define an operator phi squared by its matrix element given by the sum of those diagrams. Okay? So, what we shall do is that we shall define an operator at the point x by these diagrams only. Okay. And what does it correspond to, in fact? It corresponds to state that in any, now let us consider now a more general object where you have, in fact, now positive. Some point here I have those 2 points x and y, okay, and on the other end I have my external legs, on z1 and zn, okay. So now I'm considering the same kind of diagram, but with a general number of legs. You realize that when you apply big theorem, in fact, you always have two contributions. You have one contribution when you apply big theorem and take as a pairing x between y, and then you have z1 n, and then you have the sum over all other pairings, where x is connected to one of the z1 zn, I don't care which one, and y, therefore, the point y, is connected to another of the z's because it cannot be connected to x. So you see, you can always separate the sum over Feynman diagrams, which gives this matrix element, as the sum of this Feynman diagrams, those Feynman diagrams, where you can have all possible pairings between the z's, and the sum of the diagrams where we connect x to one of the z's, y to another of the z's, and all the remaining n minus 2 z's between them. So we have two different classes of diagrams. Okay? And you see is that now if I take the limit x goes to y, so what is this diagram? The first diagram is just, in fact, the sum over diagrams where you connect all the z's together, okay, times the propagator, namely the expectation value is the vacuum of the product of phi of x, phi of y. Okay? You see? And then you get something else, which is the sum of these diagrams, x, y. You see? And now I will just define an operator so I will define an operator which represents the sum of all those diagrams. So, I define what is called the normal product of phi of x and phi of y. That is just a definition of another operator which is defined like that, phi of x, phi of y in between those 2 points. So it's just a definition of an operator acting on the states. I define it as phi of x, phi of y equal the product of phi of x and phi of y minus the operator 1. 1 is an operator of the theory, times a number which is, well, precisely the expectation value in the vacuum of the theory of phi of x phi of y. Okay. So this is a definition of what is called the normal product phi of x and phi of y. Okay. And you realize very easily that this object, this quantity, the sum of all the Feynman diagrams which are here, or the sum of all the Feynman diagrams which are here, is just, this is just the expectation value in the vacuum of the time order product of this operator I define like that as the phi x phi y. It's just an operator. So this is an operator depending on x and y. So it's not a local operator, it's an operator which depends on 2 points in space time, but an operator, and times phi of 1, phi of e. Okay? See? So I have defined an operator by all its matrix elements. You see? But I know that if I know all the matrix elements of an operator, I know the operator. If I know all the matrix elements of the matrix, I know what the matrix is. Here is the same thing. This is a definition of the normal one. Okay? And you see that what is the advantage of this object? It is that this operator has a sense when x goes to y. Because when x goes to y, or if you prefer, when y goes to x, what's happening? You realize that this operator, phi of x, phi of y, okay, goes to something which is an operator which I will call the normal product of phi by itself as a form z, and it's defined simply by the limit when y goes to x of this object, phi of x, phi of y. Okay? And this is perfectly well defined. This is an operator which is well defined. It's well defined, it's an operator which, as an operator, is well defined because since all its matrix elements are finite.
The argument of both.
Yes?
Is that Z or should it be X or Y?
X and Y. Oh, I'm sorry, X.
I think we have a question at the back, but I'm not sure whether
Yes?
Bernard is looking with us.
Yes?
I don't understand your notation in boxes. In the first box you have X and Y and like Z on the bottom.
Ah, yes, no, I am a bit, this is all all possible contractions. And here I have only contraction like that. I'm sorry. Yeah. So my notation, no, I am right. My notation are not very consistent. Yes. Why? Oh, it's just, well, because there are circles everywhere, so there are external points. It's just that I was lazy. Why? Oh, the n, yeah, sorry. And here there is a small n and a capital N, I'm sorry. And this is the n. Okay, yes. So you see, so here it's x and y are connected, and here they are not necessarily connected. You see. Okay? So you see, by this simple trick of subtracting the singular part, we define an operator which, as an operator in the Hilbert space, is perfectly well defined. All its elements. Okay. And okay, so I have an operator which is perfectly well defined. And then, in fact, you realize not only that this operator is well defined, but that if you take the derivative with respect to y, for instance, if you consider, now if I want to consider the derivative with respect to y in a direction mu of this object, you see, of phi of x, phi of y, okay, in the limit when y goes to x, it will be an operator which I will define by the normal product of phi with d mu of phi at the point x is also well defined. Okay? So you can define not only the product of two operators, but the products of an operator with its derivative at the same point. You see, because this will contain just derivative of the propagator at the points which are different, etc. So you can define in the same way, etc. You can define in general by the same procedure d mu1 d mu k of phi times d mu d nu1 d nu L of phi at a given point. This is perfectly well defined. So you can define an operator which will be called the normal product of derivative of arbitrary derivative of two fields. It's also perfectly well defined by this receipt. You see. Okay. Okay. And this operator, you see, this normal product operator, what is the difference of between this operator and the operator we started from? It is that this operator is perfectly well defined. So I have defined an operator, let me write it here. I have defined an operator which is basically normal product of phi square rho z, which is just the operator which is not well defined, phi of z squared, minus 1 times the expectation value of the operator phi squared at the point C. This is the standard compact notation for this operator. You see? That's a compact way to write how I have defined this normal product of the operator phi with itself. You see? Okay? And what are the Feynman rules? The Feynman rules for computing expectation matrix elements of this operator. It's simply that this operator is represented by the fact that at a point x you have two legs, but you have to subtract everywhere this object. So each time that I want to compute a matrix element of, so I want to compute now, for instance, the matrix element of something where I have here this operator phi square at the point x, and other elements here, z1, zn. Well, the rule is that I simply have to compute all the possible contraction between an ordinary phi squared with z1, but I subtract the dangerous term here, Zn, so that in that case, for instance, I get only those terms and not these terms. So we see. So the Feynman rules for computing matrix element of phi square is just do not take into account any diagram like that when you apply Wick's theorem. You see? Okay, so this seems a bit formal. Oh, I'm going slowly. Very, very slowly, but that's important. Once you have done that, in fact, what's important is that, in particular, you see that if you are interested into writing matrix element of products of two operators, phi of x, phi of y, okay, and you are interested in what's happening when y goes to x, so you are considering an operator like that, elements of a matrix operator like that, you see that you have a singular contribution, which is the Feynman propagator of x minus y times the operator identity. This is the identity operator located at a point x. I can put the operator, the identity operator, everywhere because the identity operator acts, do nothing. Then I have this operator phi of x squared, phi square of x, and then I have subdominant term coming from those terms which are of order x minus y, x minus y squared, etc. Okay? You see? Okay, so now can we do the same thing? So we have defined, we have found a way to define an operator which has the properties that we expect from the product of two field operators, which do not have this dangerous infinite part. And it is simply given by this recipe. We define phi square of x as a limit of this, with this defined in this way. Okay, and that's a perfectly well-defined operator acting on the space of the space of state of the theory. Yes.
So you just wrote phi of x times phi of y, as y goes to x becomes the Feynman propagator x minus y.
Yes.
The identity.
Yes.
How can that be if y goes to x? I don't understand.
How can that be?
Well, you still have an x minus y there. But if they become equal.
But if they become equal, this becomes infinite. But we know that this product of operator has matrix element which becomes infinite too.
Okay.
You see? Simply, I am stating that all all the infinities contained in the matrix element of the products of those two operators are contained in a single function times a single operator, which here is very simple because it's the identity operator. Yes?
In the limit y goes to x, that is when y is close to x, then
Yes.
you have the expression looks like this. So it's
Yes.
in a region around where, in a region of y which is near x.
Yes.
It breaks down like this, but it's not above
Yeah,
that limit.
yeah. So the point is that so it's when y is close to x, y is close to x, we have such an expansion with terms which are subdominant here, which are contained by those operators, which are more complicated operator involving the derivative of the field. You see. And at the moment, I will need only those terms, but they are subdominant terms involving other local operator. Okay? And in fact, it is just the starting point of a very, very, very deep structure of the product of operator in quantum field theory. So now I will go a bit faster because I'm quite late, but it's important to understand how this works for a product of two operators, because then you have basically understand what one should do in general. Okay? So now we can do, you can ask the same thing. Can you define the products of, for instance, four operators? Can we define the products of four operators? We know that this is infinite also. It's infinite because we know that among the matrix element of phi 4, you get diagrams like that and diagram like that, which contains infinities. Okay? But we can apply the same recipe. When we compute the expectation value of, so imagine that you have something where you want to compute a matrix element where you have four operators, x1, x2, x3, and x4, and some other z's, z1, zn. Okay, and here you have all connected, all pairings possible. Okay, you know that you can decompose that into terms where you have the Wick theorem here. You connect x1 to x2, x3 to x4, and all the other ones are connected. Okay, and that's a very dangerous term. You have, in fact, two other terms obtained by connecting x1 to one of those three. Then you have a slightly less dangerous terms where you connect x1 to x2, but x3 and x4 are somewhere connected to one of the z's. Okay? And of course, then you have six possible terms which are similar. And then you have a contribution where all the x1, x2, x3, x4 are connected to some of the z's. Okay? And so this term is dangerous. You see? This term is dangerous. This term is dangerous. But this term is not dangerous, and this term is not dangerous. You see? So this term is fine. This term is fine. This term is fine. Okay? But these terms, so this means that I'm interested in computing what's happening when I have a product of four operators, phi of x1, phi of x4. What's happening when all the xi goes to a given point z. So now I have 4 points. You see, I have 4 points, x1, x2, x3, x4, and I'm interested in what's happening when the products of those 4 operators, how it behaves when x1, x2, x3, and x4 goes to the very same point. And you see that here I have a dangerous term, but I have a dangerous term which is proportional to the operator 1, because the non-dangerous term is just an expectation value of products of phi of z1, phi of z1 times nothing, because this factorized. You see, so this is, I have something dangerous times the operator 1. Here I have something dangerous times a matrix element of an operator which, when x3 goes to x4, is nothing but the operator we computed before, phi square at the point z, because here I have, when x3 goes to x4, I got just this operator. And then I have another operator which I can define as phi 4, the normal products of phi 4 of z. You see? So in fact, I can define exactly in the same way an operator which is a normal product of the product of 4 operators at a given point z as a limit when x1 in x4 goes to the same point x of phi of x1, phi of x4, minus the dangerous term, which is phi of x1, phi of x2 times the products phi of x3, phi of x4. Okay, plus 5 other terms. Okay, and minus and this is there is a I have the normal product here, and minus yes, that's it, minus the products of the two propagators, the expectation value of phi of x1, phi times 2 times phi of x3, phi of x4, plus 2 other terms, okay, times the operator 1. And this operator, okay, this operator is just a normal product of 4 phi operators. And this operator is also well defined. So all its matrix elements are well defined. Okay? So, and this goes on. So you can now construct, normal products of an arbitrary number of fields using this recipe, which is simply subtract all the dangerous parts which are given by these diagrams. You see? Yes? Yes?
How is it clear that by introducing an arbitrary number of key operators, we are considering all possible matrix elements?
Okay. So, first, in fact, you have seen that in the canonical formulation. So when you quantize by canonical quantization the free field, in fact, that's something you can show very easily. Because remember that a field operator phi is just a Fourier transform of a linear combination of creation and annihilation operator for one particle state in a given momentum state. You see? Okay? So basically, if you apply on the vacuum a single field operator, you can either stay in the vacuum or create a one particle state. You see? Now if you apply, so you create a linear combination of one particle state in some state of momentum. Okay? So if you now take a superposition of operator, field operator at various points, you create some superposition of one particle state of your theory. You see? Now, start to apply another phi operator at another point. You can. So it's a combination of creation and annihilation operator. Therefore, you can fall back into the vacuum or create a two-particle state. You see? Apply a third phi operator. You can create a three-particle state, create one particle state, etc. So by taking adequate combination of products of phi operator, you can construct states of the theory with an arbitrary number of particles in an arbitrary momentum state. If you work out a little bit the algebra, you realize that in that way you can construct all the states, all the vectors in the Fock space of your theory that way. So that's, you see, so that's how it works. So that's one way to see that. You have to work more to see that it works also in, for instance, in the functional interval formalism, but it works. You have enough operators if you are putting operators everywhere in space and multiplying them to create all the vector space, all the states, the possible states on this.
Is this time ordering normal ordering?
Yes.
Is that equivalent to say that it's just the operator minus the expectation value in the vacuum of the old field?
For this operator, yes. Because you see, in fact, basically, for this operator, it's phi squared minus...
I'm saying for a general operator, not just...
for a general operator, no. Because you see that, for instance, that phi squared, defined in that way, phi squared is defined as, let me check exactly the form. When you have a product of four operators, what you have is that, yes, here it is. If you work this out, you find that phi 4, well, I will write it here. You get that the phi 4 at the given point z is given by phi 4 of x, so phi of x to the power 4, let us say, minus, if you combine, minus 6 times the expectation value of phi squared at the point x times phi squared of x squared minus 3 phi square of x, and minus phi square of x is in fact phi. By x, applying x theorem, this is phi of x 4 in the vacuum times the identity. So you see that this operator is finite, this operator is infinite, but if you subtract just its expectation value in the vacuum, you still get something infinite. This thing is infinite is proportional to the operator phi square of x, which is divergence, times something which is divergent. So you have to subtract another divergence in order for something which is finite. So it's more complicated. It's only for the product of two operators that you should subtract vacuum expectation value. Expectation value in the vacuum, you get something which is finite. Okay.
Any more questions?
Yes? Yes?
So, in the 5 to the 4th normal ordering, you said that the last term is a vacuum, but what's the other infinite term? What is the meaning?
Sorry, I'm not sure I understand your question.
So that equation, you have three terms. The first term is finite, and what's the physical meaning of this term?
This is the expectation value in the vacuum of the theory. You see? So this is an operator. Okay, this is an operator. This is an operator. This is the expectation value in the vacuum omega of the theory, and this is an expectation value in the vacuum of the theory. So that's a number, that's a number, that's an operator, that's an operator, that's an operator. Is that, you see? Yes?
Should you say that you have a normal ordering on the fly?
Well, using this relation, you can rewrite it as a product of the term, which is the normal ordering, times something which is divergent, which that we can recast here. So you can do both.
No, but by the expression that you have down there, you have the force fields at the same point, and then the expectation value of phi squared, and then the normal order.
I think the formula here is correct, if my notes are correct, without normal order. But I might be oh no, you are right. In fact, here you should take phi squared. Okay. Something like that. But you can rewrite it. You can rewrite this as well, you can using this relation, you can write this either with normal products or not normal products. That's the same. Yes? Yeah? Pardon?
In the last term, proportional to the identity, we had 3 terms.
Yes.
So why did you
So
do that?
I default those 3 terms as the expectation value in the vacuum of the 4 operator, and I can apply the big theorem. This is equivalent to 3 times square big theorem. Okay. So okay. So you see that you can define operators which are more complicated operators, which are perfectly finite at a given point in space-time using this normal product algorithm. Okay. So now for one last comment. What is the relation between this definition of these operators and what you have done in canonical quantization? In canonical quantization, you have seen that you can define products of field operators, or products rather of A of K and Z of K operators, creation and alienation operator of one particle of particle states of the theory. By what is called normal ordering. We define the normal ordering product of some A dagger, etc. as just putting all the creation of operator to the right and all the annihilation operator to the left. You see? Which is another way to define products of operator. It turns out that for the free field, only for the free field, when you do that, as far as I know, normal products equals normal ordering. See? So what I've been doing, just using operators and without specifying out what are the value of these operators, I've been doing something which is equivalent to the normal ordering of products of operators. But, and then I will just spend a few minutes, a few seconds to explain that. The point is that what is important is the relation I wrote before. Because the relation I wrote before tells us that the relation I wrote before tells us that, for instance, when I am computing the products of two operators, phi of x and phi of y, when y goes to x, I have seen that there is a term which is a function which is singular when x goes to y times a number, plus something which is phi square of x, which is an operator, which is those operators are well defined, plus some term of order x minus y, some subdominant terms. What you can show, in fact, is that now you can play the same game, for instance, by computing. You are interested in what is, for instance, how do behave the operator phi square of x times the operator normal products of phi square at point y when y goes to x. See? And it's an exercise to show that you can play the same game. Play the same game. Separate the singular terms when x goes to y from regular terms. And what you get is, in fact, that, for instance, and that's something I think you will do in tutorial, is that you find that there is a Danshos term which is proportional to the square of two propagators times the operator identity, and I think it's a factor 2. And then you have a factor 4 times a single propagator times this very operator phi squared of x plus just the operator which is normal products of phi 4 plus plus terms of order x minus y. Okay, it's a bit unclear. So you see that, in fact, when you are considering now products of operators at coinciding points, you can always write the same kind of decomposition. You have a sum of a singular function, so it's a coefficient, times a well-defined local operator. And what does this mean, this relation? It means that if you take the expectation value of the products of those two operators in any state of the theory, or if you include it in some more complicated vacuum expectation value with other fields, you will always have this relation. You see? You can always write the products of two operators at two different points, where those points come close together. You can expand it as a sum of coefficients times operator. And that's what I will end up with, a very general formula, which is that in fact, for any operator A of x and B of y of the theory, here's the full field, you can always write that the product of A of x and B of y can be written as a sum over operators C of the quantum theory times when y goes to x times some function that I will call C with a capital C because it's a function which depends on A, on B, and on C. It's a function of x minus y times an operator C located at point x. So this is an operator. Okay. This is a function which is in general singular when y goes to x. Okay. And what does this mean? Those are operators. Those are products of two operators. Okay? So it's a function which tells you that if you compute the expectation value in the vacuum of the time-ordered product of the products of those operators A of x, B of y, and times some other operators, let us call it phi of z1, phi of zn. Okay? This matrix element in general will be singular when x goes to y, but you can always write it, this object as an expansion times, so sum over operators C. C are operators of the theory, times a function CABC of x minus y, and times another vacuum expectation value of the operator C at point x times those observable phi of z1, phi of zn. You see? So this is always a coefficient, a function. Okay? This is a vacuum expectation value of operators. It's a matrix element of this operator. And this is a matrix element of the operator C. So this is, in fact, a matrix element of the operator C. And this is a matrix element of the operator A of x times B of y. And this operator C is a local operator. Local, since it's associated to a given point in space-time. You see? And in fact, this relation that I showed explicitly just for the products of the two operators, that we will look at it a bit more carefully when you consider the product of two phi squared operators, is in fact a very general formula. You can show it easily for the free field theory, because you can define all the operators of the theory in the free field theory. You can, with much more work, show that it's valid in perturbation theory in any well-defined quantum field theory with interaction. But it is expected to be valid in any quantum field theory. And this formula is called the formula of the short distance. In fact, it's a short distance expansion of products of operators. You see? I consider the products of two operators, two metrics of the theory, and I look at how these products of two operators behaves when x goes to y, and I discover that I can write an expansion formula as a sum of local operators at the point where those 2 points come together, times coefficients, function. You see? And the functions I computed here in the free field theory are just propagators or products of propagators. So I can compute those objects. And all the short distance singularities, all short distance singularities are contained in the coefficients C, A, B, C. You see? So, in fact, the short distance behavior of a quantum field theory is contained in the coefficients of this short distance operator product expansion. So if you know those functions, which are functions, those are not operators, not complicated operators, matrix elements. Those are just functions. You know, you can master what is the short distance behavior of products of operators in a field theory. You see? Okay, so thank you. Yes?
We drew Feynman diagrams for these
Yes.
normal ordered products, and we use the normal ordered products to calculate physical things.
Yes.
But that means when we calculate the physical things, we just drop the term in the extension.
It means that, well, no, what I'm saying is that in order to compute something which is finite in a quantum field theory, you have to use operators whose matrix elements are finite. Otherwise, you are computing something which doesn't exist.
So we reverse engineer. We say we know it must be finite, so we leave
know
out the
it must be finite. So here is a way to construct an operator which is finite, in the sense that all its matrix elements are finite. And if I know a large enough collection of operators which are finite, like the identity, the normal products of two operators, the normal products of four operators, and then you can, in the same way, construct the normal product of 6 operators. You can also construct the normal product of 3 operators, etc. Once, if I know that I'm able to compute those operators which are finite, in fact, now, by taking combination of those operators, linear combination, I construct the algebra of all the observables of the theory. And that's enough. What?
I would go and calculate the normal ordered product.
Yes?
The rest is infinite, and then I just leave out the infinite part.
Yeah, so in fact, the way to compute that is to understand how you can leave out the infinite part in a consistent way. And you see that the consistent way to leave out the divergent part, or the singular part, is contained in the operator product expansion. This is the operator product expansion. Because you see, here is an operator which is well defined, the product of two operators. I know that when y goes to x, it has singularities. These singularities are contained in these terms, which is the first term in the operator expansion. So here I have an operator where the operator A is just phi, the operator B is the same operator phi, and here the operator C is just the operator identity. You see? So this term is the first term in the operator product expansion, where the operator C is the operator identity. Okay? And so I know that the most divergent, the most singular term in the short distance expansion of these products of those two operators is contained in these terms. And I know that the rest is finite.
But how are you?
So one way to define a product of two operators is finite is to subtract from this part. But so I subtract from this operator a singular function times an operator, and I know the rest will be finite.
But how can you be sure that it is the finite thing you're looking for?
How can you be sure that it's finite?
No, that is the particular finite thing that you want.
No, it's one particular thing that I obtain in that way. And with that one particular thing, for instance, with that particular thing, I can compute things I am interested in. For instance, I know that in a free field theory, phi operator acting on the vacuum creates one particle state. It doesn't create two particle states, but it creates one particle state. And I want an operator which creates two particle states out of the vacuum. Here is a way to construct one operator creating two particle states from the vacuum. It's not the only one, of course, but it's one operator creating two particle states, and out of this operator, in fact, you can construct all the operators. Out of this operator and those operators, you can create all the operators which, acting on the vacuum, create two particle states and one particle state. And that's enough to define, to start to construct your quantum theory, you see? Operators, you know, there are no particular operators in a quantum theory. You have a state of states, you have a state of observables, and you simply ask, if I am doing some measurement, I have some big measurement apparatus, what is the operator which corresponds to the measurement I am doing? And let me find the basis of observables so that I can express the observable corresponding to the measurement I am doing in terms of those operators. So here is the first basis of operators. So I start to construct out of the field operator, I can start to construct other operators acting in a more complicated way on my Hilbert space, and here creating two particle states. Phi 4 creates four particle states. You can, of course, define the normal product of two phi squared, which creates two particle states, etc., etc. And that's enough. You see? Okay? Well, I think it's time for coffee.